Now that we know how to compute antiderivatives, we can solve what are called simple differential equations. In this video, we will define differential equations. We will define the solution of a differential equation. We'll discuss what an initial value problem is and what an initial condition or set of initial conditions is. A differential equation, first of all, is an equation containing the derivative of an unknown function. Our goal when solving a differential equation is just to find that unknown function. In algebra, you learn how to solve simple equations like x squared equals 4. Say our goal is to solve for x. In a differential equations class, we have a differential equation like y prime equals 3y. Our goal is to solve for y of x. Now, a function that satisfies that differential equation, so that if you substitute it into the left-hand side and it equals the right-hand, if you substitute that function to the left-hand side and the right-hand side, they're equal to each other, it's called a solution of the differential equation. Now, since we have our basic rules for computing the antiderivative of a function, we can solve simple differential equations. So if we have a differential equation of this form, let's say dy dx, that's the derivative of y with respect to x, equals f of x, where f of x is a known function, we can easily find y. We say, okay, well, what does y have to be so that the derivative is f of x? Well, we just take the antiderivative of both sides with respect to x. The antiderivative of the derivative is the original function. So we'll call that y of x. And so we'll just get the antiderivative of f of x. That's going to give us a family of solutions. We call that the general solution to the differential equation. So here's a simple example. Let's say we've got dy dx equals 3x cubed minus 2x squared plus x minus 4, all divided by x squared. Well, then y is the antiderivative of the derivative, because those functions are differentiation and anti-differentiation undo each other. They're inverse operations. So it's the antiderivative of this 3x cubed minus 2x squared plus x minus 4, all divided by x squared. Now, we don't have a quotient rule for antiderivatives, so we have to do something in order to evaluate this antiderivative. We always ask ourselves, do I have a rule for that? And in this form, I don't have a rule for that. I've got to do something else first. But I notice that I've got one term in the denominator and 4 terms in the numerator. So if I take each of those 4 terms and divide by x squared and then simplify, I should be able to use either the power rule or maybe the logarithm rule for each of the terms, and we'll be able to figure out what y is. So we've got a number of terms in the numerator. We call this separating the numerator. Because if I had, let's say, 1/3 plus 3/3 or 4/3, the denominators are the same, you just add the numerators. Well, you can do that backwards as well. So if I've got a over c plus b over c, that's a plus b divided by c. And if I have a sum in the numerator, I can just separate those and then simplify each of those expressions. So that's what I'm doing here. I've got 3x cubed divided by x squared minus 2x squared divided by x squared plus x divided by x squared minus 4 divided by x squared. x squared goes into x cubed, x times. So two of those x's cancel and you just have that one x in the numerator. The x squared is reduced here. Now one of the x's will reduce there and we'll still have an implied one in the numerator. And this x squared in the denominator, we'll probably rewrite that as well because we don't have a rule for that yet. We've got 3 times x is our first term, and we do have a rule for that. Then we have a -2 as our second term. We have a rule for that. We've got a 1 over x as our third. We have a rule for that. And this -4 over x squared, we can think of as a constant times x to some power. That's -4 over 1 times 1 divided by x squared. And 1 divided by x to the n is x to the -n. So we can bring that x squared up to the numerator, call it x to the -2, and then that's multiplied by 4, and then we'll be able to use the power rule for that. Then we just use a power rule. There's an implied one here. When we compute, or for this guy, we use the power rule. The antiderivative of a constant times x is that constant. And then when we take the antiderivative of x to some power, we add 1 to the exponent and divide by the new exponent. Dividing by 2 is the same as multiplying by 1/2. And I'll write that as a 3 over 1, so we can multiply straight across. The antiderivative of a constant is a constant times our variable of integration, in this case, x. The antiderivative of 1 over x is natural log of the absolute value of x. And then we bring the -4 down, and then we use the power rule for this. The antiderivative of x to the -2 is x to the -2 plus 1. So we add 1 to the exponent and then divide by the new exponent. Then don't forget to add your c. Then when we simplify those coefficients, we've got 3/2 of x squared minus 2x plus natural log of the absolute value of x plus 4. And that x to the -1 can be rewritten as 1 divided by x. Typically, we like to write our final answer with positive exponents only on the x, on the expressions involving x. We're fine with negative exponents when the base is a constant like e or 3 or something like that. And then we can think of that as 4 over 1, multiply straight across, and we've got 4 over x plus c. And that is the solution to the differential equation. Now, because the differential equation was so simple, it was just y equals this function. This turns out to be the general solution. All of these functions for all of the possible values of c from any real value of c will do satisfy that differential equation. So if I take the derivative of this, I will get something that's equivalent to this when I'm done. If we want to check, we can. The derivative of y with respect to x is 3/2 times the derivative of x squared. Using the power rule, we bring the power down, multiply by x to the 1 less power. The derivative of a constant times x is just the constant. The derivative of natural log of the absolute value of x is 1 over x. And the derivative of that piece is easier if we rewrite it. Bring that x up to the numerator, call that an x to the -1. And then of course the derivative of c is 0. These 2's reduce and we end up with a 3x here minus 2 plus 1 over x. And the derivative of this requires the power rule. So you bring the power down, multiply by x to the 1 less power. And then if we simplify, we get this. Question is that equivalent to our original integrand? Well, I think it is. It's equivalent to what we have right here, right? And this came from simplifying that expression. So provided our algebra was correct from here to here, and we did get the right thing, the derivative of our function is this function. So we have solved the differential equation. This solution, this family of solution contains all possible solutions to the differential equation. A family of solutions that contains all possible solutions to a differential equation is called the general solution. The one solution that contains them all. Let's see. All right. Now, talked about what a differential equation is and what a solution is. It's just a function that satisfies the differential equation. So if you differentiate it, you substitute it into the left-hand side of the equation, it equals the expression on the right-hand side. Just like solving this for x gives us x equals plus or minus 2. How do you know that x equals 2 is a solution? Because 2 squared equals 4 and negative 2 squared equals 4. So the left-hand side and the right-hand side are equal when you plug in those x values. Now, when we solve the differential equation, we get that family of solutions. If it's a first order differential equation, we're going to have a family of solutions with one constant in it. If it's a higher order differential equation, we're going to have more than one constant. So if this was second order, I would have to anti-differentiate twice. Each time I do that, I'm going to get an extra constant of integration. If this was second order and I had a function over here, I'd take the antiderivative and I'd have a C1 in it, and then I take the antiderivative again to have a C2 in the answer. So I have two arbitrary constants in my solution. For an nth order equation, in general, we have n arbitrary constants in our solution. An initial value problem is a problem consisting of a differential equation and what are called initial conditions. So let me write that down on the next page. This is a problem consisting of a DE and some conditions on the solution of the differential equation and its derivatives at a particular x value. So if we have an nth order differential equation, if it's relatively simple, it might just be a function of x. In order to get y by itself, I'd have to anti-differentiate n times. So I'm going to have n constants of integration then, c sub 1, c sub 2, c sub 3, all the way through c sub n in the general solution of that differential equation. If I have this differential equation subject to these initial conditions, then we have what is called an initial value problem. We might know y at x naught. We might be told that that's equal to y naught. And we might know y prime at x naught. We call that y1. And then we'll have all of the derivatives up to the n minus 1th derivative at x naught. We'll call that y sub n minus 1. And so there are n conditions here. We call those n initial conditions. And those initial conditions allow us to find the values of those n arbitrary constants. Now, what makes them initial conditions as opposed to what are called boundary conditions is that y and y's derivatives are all specified at the same value of x. So I know y at x naught, I know y prime at x naught, I know y double prime at x naught, all the way up to the n minus 1th derivative at x naught. We call them initial conditions because often this independent variable is time. And we might know at time t equals 0, we know the y value is a particular value. We know that the derivative at t equals 0 has a particular value. So that initial conditions refers to sort of a temporal variable. We still use the same terminology when our independent variable is a different form, if we call it x or something else. It really doesn't matter. What does matter when you're actually solving the equation is the fact that all of those derivatives are specified at a particular value of x, the same value of x. Then we call it initial condition. So if you want to solve an initial value problem, the first thing you do is you solve the differential equation and you find that general solution. Now, in the differential equations class, rather than having a function of x over here, you'd have a function of x and y. And so you'll learn a lot of different methods for solving that differential equation if this is a function of x and y rather than a function of x. Or if this is the nth derivative, this would be a function of x, y prime, y double prime, all the way up to the n minus 1th derivative. So we'd have all of those derivatives, or a function of all of those, the independent variable and all of those derivatives of the dependent variable is equal to the nth derivative. But in this class, in Calculus 1, when we're learning this for the first time, this is just a function of x. And provided we can take the antiderivative of this function of x using the techniques from the previous section, we just do that n times to get y by itself. So we'll say for this type of differential equation where the right-hand side is a known function, and we have a basic rule or can use algebra to rewrite it so that we have a basic rule for computing the antiderivative. To solve this, we'll do this. We'll say to solve an initial value problem. First, anti-differentiate n times to find y of x. And that will have n arbitrary constants of integration. Every time you take an antiderivative, you get a constant of integration. We'll call them C1, C2, all the way through C sub n. Then once you have that, you will have to differentiate y n minus 1 times, so that you have y prime all the way up to the n minus 1th derivative. Evaluate y prime and all the way up to the n minus 1th derivative at x naught equals, or x equals x naught, and set the results equal to y sub 0, y sub 1, and y sub n minus 1. These x values are known, and these y values are known as well. So what you're going to end up with after you evaluate those functions at x naught and set the resulting expressions equal to these y values is just equations involving that c sub 1 through c sub n. So this is going to lead to n equations with n unknowns, c sub 1 through c sub n. So then you will solve that system of equations. And it's usually just a linear system. It's super easy. For c sub 1 through c sub n. And once you have that, you substitute those c values into the solution that you found in part 1. The solution from part 1 was called the general solution. And we'll abbreviate that GS to obtain what's called a particular solution. A particular solution is just a solution that doesn't have any arbitrary constants in it. We'll call that a PS. We'll define that particular solution. It's the solution to the equation without any arbitrary constants. So this is really relatively easy. You just have to know how to compute that antiderivative. And it's helpful, of course, to understand the terminology, which is why we're talking about the terminology today. So if I ask you for the general solution, I'm asking for that family of solutions. If it was a second order differential equation, it would have 2 constants of integration in it. And then if we have an initial value problem, if it's a second order equation, I'm not just going to give you the differential equation. I'm going to tell you when x equals x naught, the y value is this. And when x equals x naught, the y prime equals that. And we'll be able to substitute x naught and y sub 0 and y sub 1 into the original function, or excuse me, the general solution and its derivative. And that'll give us a relationship or 2 equations involving C1 and C2. Then you'll solve your system of 2 equations with 2 unknowns for C1 and C2. So you have some numbers for C1 and C2. You plug those into the general solution to get the particular solution, and then you're done. The particular solution is the solution from that family of solutions that satisfies all of those initial conditions. So it has the right values of the function and the derivative at that particular value of x. So it's the function that we're looking for. When we solve this, we find a family. When we solve this subject to this, we're finding that particular member of the family that has these characteristics. So we know that the function passes through the point x naught, y naught. We know that its slope at x naught is y1. We know that its second derivative at x naught is y sub 2, and so on. So it's super simple. Let's do a simple sort of physics application. So let's talk about projectile motion. Let's say we throw a ball up into the air. With initial velocity v naught from height y naught. And assuming the acceleration due to gravity is g, find the position of the ball as a function of time. Okay, so we know acceleration and we're asked for position. Now remember from previous sections that if y of t represents position, then y prime represents velocity, and y double prime represents acceleration. So when they tell us that our acceleration due to gravity is g, which can be either that negative 32 feet per second squared or that 9.81 meters per second squared, well, they're telling us y double prime. So that's our differential equation. If y double prime is equal to g, or alternatively, if you prefer Leibniz notation, the second derivative of y with respect to t is g. And we've got some initial conditions. Since it's a second order equation, I expect two initial conditions. Y at time t equals 0 is what? Well, we threw the ball into the air with an initial velocity of v from a height of y naught. So at time t equals 0, the height was y naught. And the velocity, which is y prime at t equals 0, was given to be v sub 0 or v naught. And so we've got a differential equation subject to two initial conditions. This is an initial value problem. It can be solved relatively easily by just taking the antiderivative. So we have the second derivative of y with respect to t equals g. So the first derivative of y with respect to t is the antiderivative of the second derivative of y with respect to t with respect to t. We've got the antiderivative of g with respect to t. That's going to be that constant times, or the antiderivative of a constant. It's our constant times our variable of integration. Instead of an x, this time we've got a t plus our constant of integration. Now I called that C1 rather than C because I have to anti-differentiate again in order to get y by itself. So I know that dy dt, which is the velocity, is gt plus C1. And if I want to get y by itself, I need to take the antiderivative of y again, or take the antiderivative of the derivative. So we're taking the antiderivative again. And the antiderivative of the derivative is the antiderivative of gt plus c1 with respect to t. And so we get, well, g is just a constant, and this is a t to the first. So we're going to have to use the power rule. So we remember, add 1 to the exponent, 1 plus 1 is 2, and then divide by the new exponent. Dividing by 2 is the same as multiplying by 1/2. And then we have the antiderivative of a constant with respect to t. The antiderivative of a constant with respect to t is that constant times t. And then we always have a new constant of integration. So y of t is equal to this. This is the general solution of the differential equation. Got two constants of integration because it was a second order differential equation. I get one constant of integration every time I anti-differentiate. Now you might say to yourself, I don't want the general solution. I want the solution corresponding to an initial height of y naught and an initial velocity of v naught. Well, I can find that values of C1 and C2 that cause my initial height to be y naught and v naught by evaluating my function at t equals 0 and evaluating the derivative at t equals 0 and setting those results equal to y naught and v naught. So y evaluated at 0 is 1/2 of g times 0 squared plus C1 times 0 plus C2. Turns out I just have a bunch of zeros plus C2, so I get C2. And we set that equal to y naught. So I have a simple equation, C2 equals y naught. Normally I would solve that for C2, but there's not really much solving to do. And then y prime at 0, that's the same as dy dt evaluated at 0. And dy dt was this gt plus C1. So I've got g times 0 plus C1. That's just C1, and we set that equal to V naught. So C1 equals V naught. So what is the solution to the initial value problem? Well, it's this general solution. But then I substitute in C1 equals V naught. And C2 equals Y naught. If you recognize this equation from physics, that's a good thing. That's our equation for projectile motion. Yeah. It was relatively easy to find. All we had to do is anti-differentiate twice. And this is assuming that we're just standing here with a ball. We throw the ball up with a particular velocity V naught. And then we're experiencing acceleration due to gravity, which is this negative g. And the ball is initially at height y naught. So maybe our y-axis looks like this. Maybe y equals 0 at the floor. And then at time t equals 0, we're throwing it from y naught with velocity v naught. And then this is our y value. Now this is a particular solution because v naught is known, that's usually given to us. Y naught is known, that's usually given to us. Gravity is known as long as we know where we are and what units we're using. Usually it's that negative 32.2 feet per second squared or negative 9.18 or 9.81, sorry, meters per second squared. And this solution to the differential equation is called a particular solution because it's a solution that doesn't have any arbitrary constants in it anymore. V naught, Y naught, and G are going to be known in general. So this is the equation describing projectile motion in one dimension. So we're just throwing the ball up and then it's coming back down. All right, so here's another example. Let's say we've got the differential equation equals, or the differential equation is given to be y double prime equals x plus sine of x. And maybe we have some initial conditions as well. And I don't know what I want those to be yet. So I think I will say y at 0 equals some number and y prime at 0 equals a different number. I actually need to compute the antiderivatives before I know which numbers will make a nice, pretty answer. So if I had those numbers, this would be called an initial value problem. And if I wanted to solve this differential equation for y, I would just anti-differentiate twice. So I've got y double prime. To find y prime, I take the antiderivative of y double prime with respect to x. That independent variable is implied by the function on the right-hand side. And I just apply my rules in order to compute the antiderivative of each of these guys. The antiderivative of x requires this power rule. So I've got x to the first, that's implied. We add 1 to the exponent and divide by the new exponent. So there's an implied 1 there. Add 1 to the exponent, that's 2. and then divide by the new exponent. Dividing by 2 is the same as multiplying by 1/2. And then we ask ourselves, what do we take the derivative of to get sine of x? Negative cosine of x. Because the derivative of cosine is negative sine. Negative sine times -1 is positive sine. So if I take the derivative of this, I get this. So that is our y prime. Don't forget a constant of integration. That's y prime. Now, because it was a second order differential equation, that's just the highest order derivative in the differential equation. You have to anti-differentiate twice. I guess I just used that term. Order of the dE is the highest order derivative in the equation. Since this is second order, we've got to anti-differentiate twice, and each time I get a constant of integration. So I know y prime is equal to this. That means y of x is equal to the antiderivative of y prime with respect to x. I've got 1/2 x squared minus cosine of x plus c1 here. And we bring the 1/2 down. And to compute the antiderivative of x squared, we're going to use that power rule again. Very simple. Add 1 to the exponent and divide by the new exponent. 2 plus 1 is 3. Dividing by 3 is the same as multiplying by 1/3. And I bring the negative down. You say, what do you have to take the derivative of to get cosine? It's sine. And the antiderivative of a constant is a constant times x, because the derivative of a constant times x is the constant. Don't forget your second constant of integration. Almost think of it as constant of anti-differentiation, not actually, but the term that everybody uses in all the textbooks is constant of integration. So this is our y of x. And if we multiply straight across, we get a 1/6 there times x cubed minus sine of x plus c1x plus c2. Now, if we were just asked to solve the differential equation, we would be done. This is the general solution of the differential equation. I've been writing that out, but typically I'll just write GS. The GS of the differential equation is that. Now, if I have some initial conditions, I can find the values of C1 and C2 that cause this function to satisfy not just the differential equation, but the initial conditions as well. So maybe at 0, we're going to say the x value is, or the y value is 5. And maybe at when x is 0, y prime has a y value of 3. With those two pieces of information, we can solve for C1 and C2. So y of 0 equals 5 tells us the following. When I substitute in x equals 0, and simplify, you get a bunch of terms that add to 0 plus C2. That expression involving C1 and C2 has to equal 5. Since it just tells us that C2 equals 5 this time, that's our only conclusion from that piece. Now we know y prime at 0 equals 3. That means when we evaluate y prime at 0, and y prime at 0 was, or y prime was found right here. So that's 1/2 times 0 squared minus cosine of the x value plus C1. When we evaluate that at 0, we have a 0 here, and cosine of 0 is actually 1. We have to set that equal to 3. So this equation simplifies to -1 plus C1 equals 3. So C1 must equal 4. So now that I know my C1 and C2, I can substitute those into the general solution to get a particular solution. Y of x is equal to 1/6 x cubed minus sine of x plus 4 times x. That's our C1 times x plus C2. Now, if you want to check this, you can differentiate twice. and make sure that the derivative of this is actually, or the second derivative of this is actually x times sine of x. You can also evaluate the function at 0, make sure you get 5, and evaluate the derivative at 0 and make sure you get 3. So to check, I will compute the derivative. I have 1/6 times the derivative of x cubed, which is 3x squared, minus the derivative of sine of x, which is cosine of x, plus the derivative of 4x, which is 4, plus the derivative of 5, which is 0. And then if I take the derivative again, I have 1/2 times the derivative of x squared, which is 2x. And then I have -1 times the derivative of cosine of x, which is negative sine of x, plus the derivative of 4, which is 0. So the 1/2 and the 2 reduce, and I end up with x plus sine of x. So is y double prime equal to x plus sine of x? Yes, it is. That's the original differential equation. So we know that the differential equation is satisfied. Now, if we want to make sure that our initial conditions are satisfied, we need to evaluate y at 0. So we substitute in x equals 0 here. We're gonna have 0 minus sine of 0, which is 0, plus 4 times 0, plus 5. So that's 5. And y of 0 equals 5 was our initial condition. That's good. And then we evaluate y prime at 0. So we've got 1/2 of 0 squared minus cosine of 0. So that's 0 minus 1 plus 4. -1 plus 4 is 3. And that was our second initial condition. So we have solved the differential equation. Let's look at a simple first order differential equation now, and then we'll show how we're picking out a member of that family of solutions that satisfies the initial condition. We had one with polynomial and a trig function. Let's do one. I don't know. I think we've already done one with a square root in it. Let's say we've got a differential equation that looks like this. Dy dx equals something divided by the cube root of x. Let's do 4x squared minus 5x plus 1. And then maybe our initial condition tells us that at x equals 1, our y value has a particular value. We're going to solve the differential equation to find that general solution. And then once we have the general solution, I'll pick an initial condition, and then we'll make sure that to find the right value of the constant of integration so that the function satisfies the initial condition as well. So I know that the derivative is equal to this. So the solving the differential equation just requires us to take the antiderivative of the derivative to get the original function, because the derivative and antiderivative are inverse operations. They undo each other. So I've got this 4x squared minus 5x plus 1, all divided by that cube root of x. That's an implied x to the first, and we're taking the cube root. So we can write that as x to the 1/3 power. And then we don't have a rule for that until we divide each of these terms by x to the 1/3. So I've got 4x squared divided by x to the 1/3 minus 5x divided by x to the 1/3 plus 1 divided by x to the 1/3. We do this a lot. There's an implied 1 there, so I've got a 4/1, which is just a 4, times x to the 2 minus 1/3, which is 6/3 minus 1/3, which is 5/3. Then we're subtracting 5, and then we've got an x to the first divided by x to the 1/3. We subtract those exponents, again, because x to the n divided by x to the m is x to the n minus m. We have 1 minus 1/3, which is 2/3, or 3/3 minus 1/3 is 2/3. And then or 1 divided by x to the n is x to the negative n. So this 1 over x to the 1/3 is actually x to the negative 1/3. And now I can use a power rule for each of these guys. So we will bring the 4 down, then add 1 to the exponent. Adding 1 to each of these fractions involves adding 3/3, because 3/3 is 1. So 5/3 plus 1 is 5/3 plus 3/3, so we get 8/3. And then we divide by 8/3. Dividing by 8/3 is the same as multiplying by 3/8. Then we bring the -5 down. Then we multiply by x. to the 2/3 plus 1, because we add 1 to the exponent. 2/3 plus 1 is 2/3 plus 3/3, which is 5/3. And then we divide by 5/3. Dividing by a fraction is multiplying by the reciprocal. So dividing by 5/3 is multiplying by 3/5. And then here we do the same thing. We've got x to some power. So we add 1 to the exponent. Negative 1/3 plus 1 is negative 1/3 plus 3/3, which is 2/3. And then we divide by 2/3, which is the same as multiplying by 3/2. And then we get a plus c. And I'll just say 1 plus c this time because we've already got y. We don't need a c1 and c2. It was just a first order differential equation. Now we can simplify. The 5's reduce here. You can think of that as a 1. 5 divided by 1 times 3 divided by 5. So the 5's reduced and you just get 3 divided by 1, which is a 3. 4 goes into 8 twice. So you end up with 3/2 times x to the 8/3 minus 3 times x to the 5/3 plus 2/3, or 3/2, excuse me, times x to the 2/3 plus c equals y. So this is our general solution. It's a family of solutions that contains all possible solutions to the differential equation. And we might be told that at x equals 1, the y value is, let's say, -2. Well, then y of 1 equals -2 implies the following. When I evaluate this expression at x equals 1, I've got 3/2 times 1 to the 8/3 power minus 3 times 1 to the 5/3 power plus 3/2 times 1 to the 2/3 power. But we know 1 to any power is just going to be 1. So we really are just going to have those coefficients that add together here. So I've got 3/2 minus 3 plus 3/2. 3/2 plus 3/2 is 3. So 3 minus 3, which is 0. 0 plus c is just c. We're going to set that equal to the initial condition, which is -2. That means our constant of integration must be -2. So the particular solution is the member of this family that satisfies this initial condition. And in order to satisfy this condition, our c has to be -2. So we'll have y of x equals the original function, but we replace the c with -2. And you can check and make sure this works by substituting 1 into the equation. We substitute 1 here and here and here. We get 3 minus 3, which is 0, minus 2, which is -2. So that the differential or the function satisfies the initial condition. And then if we differentiate this, the claim is that the derivative is equivalent to that expression right there. So we can do that. Let's check the differentiation. The derivative of x to the 8/3 is 8/3 times x to the 1 less power. 8/3 minus 1 is 8/3 minus 3/3, which is 5/3. We bring the -3 down. Then we multiply by x to the 5/3 minus 1. Oh, whoops, sorry, we're differentiating. So we have bring the 3 down, and then we bring the exponent down. Sorry about that. And then we multiply by x to the 1 less power. 5/3 minus 1 is 5/3 minus 3/3, which is 2/3. And then I've got 2/3 there. And then I'm using the power rule again. So I bring that power down. And I multiply by x to the 1 less power. 2/3 minus 1 is 2/3 minus 3/3, which is -1/3. And then the derivative of the -2 is 0. We simplify those coefficients. I get y prime equals 4 times x to the 5/3 minus 5 times x to the 2/3 plus x to the -1/3. The claim is that's equivalent to the original right-hand side of the differential equation. And I think it is. That's what we had as our integrand at this step. And this step came from taking each of the terms in this numerator and dividing by that x to the 1/3. So y satisfies the differential equation. And we know that y of 1 equals -2. So y, I'm going to say y equals star, where this is our star, is a particular solution of the initial value problem. All right. So I think that's it for our introduction to differential equations. We defined a differential equation. We defined what it means for a function to be a solution. We talked about what an initial value problem is, which is just an nth order differential equation subject to n initial conditions. Those are all conditions on y and the first n-1 derivatives at a particular x value. And then our goal in solving an initial value problem is to find the member of the general solution family that satisfies those initial conditions. We said the general solution is the one family of solutions that contains them all. We're always looking for that. And whenever we have a simple differential equation like these, where the right-hand side or the nth derivative is just equal to a function of x, we just anti-differentiate n times, and that will always get us the general solution for these very simple differential equations. And a particular solution is just a family or is a member of the family of solutions. It's a solution that doesn't have any arbitrary constant. And we derived the projectile motion equation as well. I do want to show you just a preview of the Diffie class. Here's a very simple differential equation. I always talk about this in the first day of Diffie. Y prime equals, let's say, 2y. We say to ourselves, okay, what function can I take the derivative of so that I get twice the original function back? Now, students in this class might be tempted to take the antiderivative of both sides, but we don't want to do that because this is a y, it's not an x. If that was a 2x, we'd take the antiderivative of both sides and we'd have y equals x squared plus c. But since it's a 2y, we've got to do something different. Say, well, what kind of function can I take the derivative of where I get a multiple of the original function? Well, it's exponential functions. Exponential functions work. If that was just a y, you say, what function can I take the derivative of? So the derivative is the original function. It would be the e to the x function, because the derivative of e to the x is e to the x. Well, if I'm multiplying by an extra 2 when I take the derivative, I think e to the 2x should work. Because the derivative of e to the 2x is e to the 2x times the derivative of the inside, which is a 2. So that's 2 times the original function. And if we've got 2 times the original function on the left-hand side, well, that's going to, or 2 times the original function is the derivative of y. Get that on the left-hand side, that does equal the right-hand side. So that is a solution. So this is a particular solution as it stands, but it turns out that I can multiply by a c, and that will still be a solution, because if I compute the derivative of c times e to the 2x, I get c times the derivative of e to the 2x, which is e to the 2x, times the derivative of the inside by the chain rule. Then the left-hand side of the differential equation is just y prime, which is 2c e to the 2x. And the right-hand side of the differential equation is 2y, which is 2c e to the 2x. So the left-hand side equals the right-hand side, and the equation is satisfied. So it turns out that this equation, or the e to the 2x, was just one possible solution to this differential equation. But we've got family of solutions. We've got infinitely many solutions corresponding to each possible value of that real number c, where c is an arbitrary real number. So we've got infinitely many solutions to the differential equation. So this is called the general solution of the differential equation. How did we find it? We just guessed. In the differential equations class, we won't have to guess. We'll have a reason why we choose that function. But the idea is the same as what we talked about here. We're thinking about what types of functions we can take the derivative of to get multiples of the original function. And these are those functions. Since it's first order, we expect one constant of integration, and we've got it. And if we had some initial condition, let's say we had an initial condition, y of 0 equals -7, well, then I know that when I substitute x equals 0 to this, that's c times e to the 2 times 0, which is just c, that should be equal to -7. So c would be -7. We'd have y of x equals -7 times e to the 2x. So this would be a particular solution to the initial value problem, consisting of this differential equation subject to this initial condition. But again, that's just one member of that infinite family of solutions. Graphically, c times e to the 2x. Well, if c is 0, we just get like the most boring solution possible. We just get y equals 0. And of course, the derivative of 0 is 0. So that satisfies the equation. That's called the trivial solution to the differential equation. There are certain types of equations called homogeneous equations. We'll talk about that in Diffie. They always have the trivial solution as a solution. We call it trivial though, because it's usually not the solution you're looking for. You're like, oh, if I plug in y equals 0 to that, I get the right thing, but that's probably not the one that I want. I'm probably looking for a member of this family that satisfies some other condition. But if they tell me that y at 0 equals 0, I have to have this solution. Turns out there's an existence and uniqueness result that says we only get one solution to this, and it would be this one. But if c is equal to 1, if we had y of 0 equals 1, we would have just the e to the 2x function, which looks like this. And if we multiply by 3, we get 3e to the 2x is also a solution to the differential equation. It's going to be 3 times as tall, still passes through that point. I don't know, I'm not doing a very good job of multiplying by 3. But for every value of c that you can possibly think of, you take that exponential function, multiply that by a real number c, and that's going to satisfy the differential equation. And because of the fact that when we substitute x equals 0, we just get c, whatever y naught is, that's what c happens to be. So if I have y of 0 equals y naught, this particular solution in that case would be y of x equals y naught times e to the 2x. And we could graph all of those solutions for all the possible values of y naught. So that's that. And of course, differential equations are very popular in physics and lots of applications. And the one example that we worked in class was this projectile motion example.